Okay, now we're going to keep going with 8.2. Using the result from problem 8.1, determine A, the closed loop characteristic equation and roots using the quadratic formula with a K. Okay, so we have this one over here. It's from the previous problem. So this is the characteristic equation with the K inserted. So why don't we use the quadratic formula real quick so we can find that the roots, oh, I don't want to do that. We can find that the roots are equal to b, which is 11 plus k, and this should be minus, plus or minus the square root of b, 11 plus k squared, minus 4 times a, which is just 1. It's the coefficient on the s squared, times 30 plus 3 times k. We close that out. We divide everything by 2 times a, which is again 1. Okay. So now that we have this, and I'll move this here. So now that we have this, what do? Well, let's create a table, because that's what they ask us for. And we want to know the roots. So as k changes, we want to know what the roots are. So they're telling us to calculate that for a k of 0, 1, 5, 10, and 100. I'm looking right here. 0, 1, 5, 0, 1, 5, 10, and 100. So how are we going to do that? Well, if I put 0, I'm going to input 0 into this formula. Basically, I'm going to use my calculator to evaluate it each time. So let's say I have minus 11 plus 0 plus or minus. I don't think I have a plus or minus sign in my calculator. I'll just do plus the square root of 11 plus 0, and I'm just setting it up for later when it's not going to be 0, minus 4 times 1 times 30 plus 3 times 0. Everything divided by 2. So I get negative 5 as one of the answers. And, well, that makes sense. I didn't even have to do that. So think about where we started. That was our characteristic equation here. So the two roots are negative 5 and negative 6. Okay, so we have negative 5, negative 6. Now we're going to do it again, but with the value of 1. So I'm just going to copy what I have, paste it, put a value of 1 in. So this should be 1. This should be 1. And this should be 1. I would suggest doing this in MATLAB. If you define a function with this is your function, and you just evaluate it at each point, then that would be way faster. And we do that. With the plus, we get negative 427, negative 4.27, and negative 7.73. And then for the other values, what we get is negative 3.64 and negative 17.59. And then we get negative 12.36. So negative 12.36. Then we get negative 3.41 and negative 17.59. And finally, negative 3.06 and negative 107.90. 4. Okay. Okay, so once I do that, what am I going to do? What am I going to do? So we have this stuff over here, and now they're saying, on the sketch of problem 8.1, plot the movement of the roots as the gain is varied from 0 to 100. So this root decreases, well, the first root, -5, increases, goes towards 0. So this root goes towards 0. The other root goes towards -infinity. So this is, and this makes sense because if you look at the book, the rule is that you will have a branch that starts when you have when you're on the left, to the left of an odd number of zeros and poles. So there's 1 0 here, that's an odd number, and then there's 1 2 3 here, and that's an odd number. And in the middle here, there's 2, so we don't have anything. Okay, so that's what they're saying. Now, where does the branch associated with the OLTF, which stands for open loop transfer function pole, at s equals -6 appear to be going? It seems to be going at it goes towards, it's approaching -infinity. How about the one at -5? It's approaching 0. Well, the 0, which is not at 0, it's at, what was our 0? At -3. What role does the open loop 0 seem to be playing? It's kind of like a magnet, an attractor. It's a magnet. Summarize these results in your own words. Okay. I hope this was clear, and I'll see you next time.